We have a cart with a magnet at some distance L from the larger magnet. We're going to release this cart from rest, and we're going to see how close it gets to this magnet before the cart comes to rest. Okay, so you can do this. You have the cart and the magnet, and it would be worthwhile doing so. Overview. Well, first of all, from an energy standpoint, the cart is going to lose potential energy and gain kinetic energy, at least for a while. It's going to gain potential energy, magnetic potential energy, so it's going to lose gravitational potential energy. It's going to gain magnetic potential energy. At first, it's not going to gain much magnetic potential energy because it's pretty far away from the magnet, and the magnet doesn't have a whole lot of influence until it gets pretty close. So we are going to have a decrease in gravitational potential energy, not much increase in magnetic potential energy. The result is going to be that we have an increase in potential energy, in kinetic energy, just as we would if the magnet wasn't there. Now, when we start getting closer to the magnet, that's going to limit how much our kinetic energy increases, because that's going to increase the potential energy of the system. Remember, you only have so much total energy. Now, implicitly here, there are no dissipative forces, no frictional force, no air resistance, just the component of the gravitational force down the incline and the magnetic force acting up the incline. So the total energy is going to remain the same by the work energy theorem. Total mechanical energy will remain constant. Again, then, with respect to distance, the gravitational potential energy on a level incline, on a straight incline, is going to decrease linearly with how far you go. Every meter you go, you're going to lose the same amount of potential energy you would in any other meter, because every meter you're going the same distance lower as with the previous meter, and that's what governs your change in gravitational potential energy. Magnetic potential energy is much more complicated, way more complicated than the simple model I use here. I note that it's not realistic, but we're going to assume here that the magnetic force is some constant over r cubed. And presumably in a situation where you have numbers, you're going to have the value of that constant. And r is the separation of the magnets. So as you get closer to the magnet, the force increases slowly at first, but then very rapidly, because that cubing function has a graph that does this. Okay. So the angle of the incline is theta. We're going to move, well, we have an initial separation L between the magnets, and we're going to summarize the work energy situation here, the energy situation. Kinetic energy is 0 at the start and the stop, because we're looking at where does this thing come to rest. Okay, we're going to declare the potential energy at 0 at the start. We could have easily declared the potential energy to be 0 when it stops, but we don't know where it's going to stop. It's simpler to just declare the initial potential energy to be 0. This, of course, means that as the cart starts decreasing, the potential energy is going to go below 0, because this is going to decrease at a constant rate, whereas this increases very slowly at first and then rapidly toward the end. Okay, so we declare the potential energy to be 0 at the start. Total mechanical energy is constant. because we're making that assumption. If the kinetic energy is 0 at the start and the potential energy is 0 at the start, then the total energy is 0 everywhere. And that's, of course, the sum of potential and kinetic energies. Now you can have negative potential energies, which would then give you positive kinetic energies. If the potential energy at the end is 0, I'm sorry. Yeah, the kinetic energy is 0 at the start and at the stop. I was looking for the stop there. Kinetic energy is 0 at the start and the stop. Potential energy is 0 at the start, so the total energy is 0 at the start and stays 0 throughout. The total energy is also, well, the kinetic energy is also 0 at the stop. So the kinetic plus the potential is equal to the total. So 0 plus the potential at the end has to equal 0. The potential energy has to be 0 at the end. That's common sense if you just think about what the quantities mean. So we're looking for the point at which the total potential energy of this system is 0. Now the total potential energy is the gravitational potential energy plus the magnetic potential energy. Okay. What we want to do is we want to figure out what the potential energy is at an arbitrary position along here. If we've got that, then we can just write the condition. Total potential energy is 0. The final kinetic energy is 0, so the sum of the potential energy, the sum of the mechanical energy and the potential energy, the gravitational potential energy is going to be 0. Okay, and that's what we're going to write over here. Okay, if we assume this, we can do some integration to get the potential energy function. Now, on this problem, I would probably go ahead and just give you the potential energy function, but it's a good activity to calculate the potential energy function. So, we want to start answering this question by finding the magnetic potential energy function relative to separation r sub 0. Now, why separation r sub 0? Well, it's separation r sub 0 because we're going to have r be the center-to-center separation of the magnets. Now, that's not totally 100% accurate because of the anomalies of magnetic fields and forces and stuff, which are very complicated and way beyond the scope of what we can do even when we study magnetism. You need multivariable calculus to even come up with a reasonable model, and even that reasonable model is going to fail to take account of a lot of things. Okay, so if r is a separation of the centers, well, the magnets have thickness, so there's only so close they can get. And that's a good thing, because if they could get down to r equals 0, you'd have an infinite magnetic force. Again, this is not a model of real magnetism, just a model we're using for convenience. Okay, so r naught is going to be how far the centers are apart when the magnets are in contact. You can't get any closer center to center than that. So we're going to calculate the magnetic potential energy relative to separation r naught. The work by the magnetic force, if you move from r naught to x, if you move from contact out to position x here, is the integral from r naught to x of the magnetic force with respect to r. R is going to go from r naught to x. Okay, r is your separation. Separation is going to go from r naught here to x here. You integrate then this function from r naught to x, and the integral straightforward. And if I did it right, there's your expression for the magnetic. Well, there's the expression for the work done, and the work done by the magnetic force as you move in this direction is negative because the magnetic force is this way. you get a negative here. Now, R naught is less than x, so the reciprocal of R naught to the fourth is greater than the reciprocal of x to the fourth. So this thing is positive without the negative sign here, but the negative makes it negative, so you might want to note that. Well, it follows that the magnetic potential energy is equal and opposite to the work done by the force, magnetic force. So there it is. There's your magnetic potential energy as a function of position x on the incline, position x measured relative to the point where the magnets would be in contact. Okay, now, as the car descends, it loses gravitational potential energy and gains magnetic potential energy. And kinetic energy. Okay, didn't mention the kinetic energy because we were focused on the magnetic potential energy. Again, I kind of repeat what I said over there. Initial and final kinetic energy is 0. The change in the gravitational potential energy from the start to position x is what? Well, I didn't do it and I didn't draw it because I try to cover a lot of things in class, but from start to x, your distance is going to be L minus x. Your displacement is going to be L minus x. Angle's theta here. Your vertical distance is L minus x times the sine of theta, just by this simple right triangle. You know, this side is opposite this angle, and here's your hypotenuse. Okay, so it follows that the gravitational potential energy change, and I'm not going to explain that, is negative mg times L minus x sine theta. Okay? mg, the weight, the force exerted by gravity, multiplied by the distance you go down, gives you this much work being done by gravity on the mass of the car, and the change of potential energies equal and opposite to that. The magnetic potential energy is what we say here. Now, I'm not sure which board we want to go to, but I think it might be this one. Okay, so from start to position x, your total change in potential energy, that's a TOT there for total, is change in gravitational plus change in magnetic, negative mg times L minus x sine theta, which we just saw here, and the a over 4 times reciprocal r to the fourth minus reciprocal x to the fourth potential energy change. From start to stop, kinetic energy is 0 at start and stop. We declare potential energy to be 0 here. It follows then the potential energy has to be 0 here. We made that argument earlier at the beginning. Okay, so if the total potential energy is 0 here, well, the total potential energy at this position is going to be the gravitational potential energy plus the magnetic potential energy. The change in potential energy from here to here is 0. So we could either say gravitational potential energy change, potential energy change, the change in potential energy is going to be this. Okay. The change in potential energy from start to position x, change in magnetic potential energy, start to position x. There's your equation. We solve that for x, and we see where the car stops. Now, mention that the car stops at this point this is not the point where the force is zero. Okay, the force is zero somewhere back here. It's got kinetic energy when it reaches the point where the force is zero, which carries it beyond the point where the force is zero. Now you've got force is zero here. Force is positive in the direction of motion from here up towards zero. Then it goes negative. Okay, it doesn't stop when the force equals zero because it's got kinetic energy at that point. It continues on and gains the gravitational or the magnetic potential energy. And now the total potential energy is zero, but the force isn't. The force is back this way. So the force is going to push the thing back up the hill. And if there's no friction to resist it, it's going to push it up the hill till the total energy, till the kinetic energy is zero again, which has to occur when the potential energy is zero, since the total energy is zero. So it's going to go from here down to here, get pushed back up here, come back down, push. It's going to oscillate, not in simple harmonic motion, but it's going to oscillate. And that oscillation will be interesting to analyze. Somewhat difficult to analyze, since some distraction happened over there. A little bit difficult to analyze since the magnetic force is really hard to model. Theoretically, we could model it. Okay, well, there it is. Now, I drew this approximate graph here. What happens to kinetic energy as you go from the initial position to the stopping position? It's zero to start, it's zero to stop, and you have a positive kinetic energy. You can't have negative kinetic energy. You have positive kinetic energy from here to here. Total energy is zero, so your potential energy has to be equal and opposite to your kinetic energy. You could graph your gravitational potential energy, which looks like this. You could graph your magnetic potential energy, which looks like this. And the difference of these things is your kinetic energy. Okay, we'll come back to the graph. But here's a better graph. Not a great graph, there's some flaws in it. Our magnetic potential energy at R0 is its maximum, and it drops off really rapidly, but then smooths out like so. And that would be like our reciprocal R to the fourth rule with the reciprocal R0 to the fourth in there too. Okay, so anyhow, that's that, and you could graph that easily. The gravitational potential energy I've drawn in purple here. Okay, as we approach the point where x equals L, that's up at the top of the incline, your magnetic potential energy is down near zero, and your gravitational potential energy has to be equal and opposite to that, because as we've established, since the total energy at the beginning is zero and total energy doesn't change, these have to be equal and opposite. Okay, so we have this, and then we have this potential energy that increases with increasing x. Of course, the card is moving toward decreasing x, so it decreases as x decreases toward its stopping point. We stop when these two are equal and opposite, when the total energy is zero. Okay, so I also comment again, net force isn't zero at the stopping point, and you got enough information you could calculate where the net force is zero. It's going to push back up and repeat, and we mentioned that previously.